Authored by veteran chemistry teacher Abdul Shakur, these two textbooks provide all the essentials that would not only enable students to master grade 11 chemistry, but to excel at the next higher level in this subject. What make these texts unique are their creativity and profundity with which concepts are explained for clarity and mastery. The following is one of a set of 44 different tutorials created by the author, using materials primarily from the text Chemistry 11 in Focus. I hope you enjoyed this video. If you liked it, please give it a thumbs up and don't forget to subscribe. We will see you in the next video and thank you for watching.
Today our lesson deals with naming binary ionic compounds. It starts on page 119 and it ends on page 126 from the text Chemistry 11 in Focus, and it covers the definition of binary ionic compounds, metal ions with standard valencies versus those with multiple valencies, naming nonmetals in binary ionic compounds, and naming binary ionic compounds on multiple valencies. Since each chemical compound has its own unique physical and chemical properties, it is essential that it be known internationally by a name that is unique to it. Up to the 18th century, there was no system of naming compounds. Some compounds were even named after places and people. It was only in 1787 that a French chemist, Guiton de Marveil, devised his classical system of naming compounds. Marveil used words from both Greek and Latin to name compounds. In his system, he named the metal of a compound first and then ended it with a suffix such as "-us" and "-ic". For example, the element iron in a compound can be named ferrous or ferric. For some compounds, the suffix can be "-ite" or "-ate, and the prefix can be "-hypo" or "-per". However, with the discovery of more complex compounds, the classical system became limited in its usefulness. For example, for some metal having ions that have more than two valencies, it fell short in its capacity to name these compounds. Vanadium can have valencies of 3+, 4+, and 5+. In the year 1919, the Prussian chemist Alfred Stock devised an alternative system of naming compounds which became known after him as the Stock system. This system uses Roman numerals in parentheses to represent the specific charges on the metal ions. For example, the name cuprous is replaced by copper 1 and ferrous is replaced by iron 2. In these cases, 1 and 2 represent the 1+ and 2+ valencies of the copper and iron, respectively. The International Union of Pure and Applied Chemistry, IUPAC, which was formed in 1920, has overseen the standardization rule for naming compounds, and its most recent revision was published in 1990 with regards to naming compounds. One of its main objectives was to ensure there is always international agreement for naming compounds. Scientists must have precise knowledge of the different elements and the number of atoms of each element that a compound is composed of. The recommendations provided allow nations of the world the flexibility of using the classical or stock systems in naming compounds. So now we go forward and show how we name binary ionic compounds. A binary ionic compound is made up of only two elements, a metal and a nonmetal. The metal, of course, is the one that loses electron to the nonmetal. In so doing, the metal becomes a positively charged ion, and the nonmetal becomes negatively charged, and they are bonded together by an ionic bond. Just a quick review, we've done this already. We just want to show you the three different methods of arriving at the formula of a compound. We're not going to go into all the details. We've done this when we did bonding already. So here you're seeing oxygen is needing 2 electrons, and each of these lithium atom is capable of giving 1 electron. So in the end, each lithium atom becomes positively charged, and the oxygen here becomes 2 negative. You can see here, you'll keep repeating this all the time, an ionic compound is electrically neutral because the sum of the positive charges here is equal and opposite to the sum of the negative charges there. So when you add these together, you end up with some charge of 0. And then you have the Lewis dot structure, which is a shortcut way of formulating the formula for the compound here. We're using dots, so here you're only using the valence shell electrons. So lithium here is going to give 1 there, and this other one is going to give 1 here. So in the end, the oxygen has the octet, and these will remain in the duplex, but you don't see. We've spoken about that already. So here you're seeing you have two lithium ions with 1 oxygen ion there, and the formula here is Li2O, because you're using 2 lithium atoms to 1 oxygen atom there. Next, you use what is called the crisscross method. The crisscross method assumes that you understand the Bohr-Rutherford diagrams and the Lewis dot system of arriving at these compounds. So here again, we're showing how you have 2 lithium ions there and 1 oxygen ion there. And you can see we're showing you here how the sum of the positive valencies on the positive ion must be equal to the sum of the negative valencies on the negative ion, such that you end up with a total charge of 0. How do we do the crisscross? They will give you the valence on the metal ion and the valence on anion. So what you do now, you make these subscripts. That 2 here, you make it the subscript of lithium, and the 1 here, you make that the subscript of oxygen. Here you see Li2O. But you don't see the 1 there because you're not putting in the 1 there, and also we're not putting in the charges. So when you have a 1, you don't put it in. So you see something like this, you'll assume that oxygen is 1. And here you have it for calcium and oxygen. The 2 goes there, and this 2 comes here, and you get Ca2O2. When these are the same here, you reduce it to the lowest one. So the formula of calcium oxide is CaO. Now the difficulty comes when you have metals with multiple valencies. Look at the part of the periodic table here and try to establish some points. Metals of group 1A, group 2A, this is 30, and group 3A, they have standard valencies. Their valencies don't change. The other metals are called transition metals. We've spoken about that already. They can have more than 1 valence. Okay? So whenever they have different valencies, they have to be named in a specific way, depending on what is the valence on the metal ion in that compound there. Let us say you have a compound FeCl2. That means you're dealing with this charge here, a 2. You will have to say it's ferrous chloride. If it were this one here, then you'll have to say it's ferric chloride to distinguish these 2 here. These, you don't have that problem. Also, these ones here, non-metal ions there, they have standard valencies. So if you memorize these, along with zinc and silver here, you will quickly be able to distinguish metal ion that has a standard valence from those that are multivalent. So I implore students to memorize these. So when you start to name compounds and writing formulas of compound, it becomes easy for you. So keep that in mind. Now let's go now and see how you name the metal ion in chemical compound. So if it were required to write the formula for calcium oxide, the only formula for that will be this. This is so because the calcium and oxygen atoms, the valence of these are fixed. However, writing the formula for the compound copper oxide will be an ambiguous task because the copper is a multivalent element with valencies of either 1 or 2 plus. So you can't say write me copper oxide, you have to be specific, because the oxides of copper could either be Cu2 or Cu2O. And now to distinguish between the various valencies of the metal ions having multiple valencies, scientists have derived a few methods of naming such metal ions in compounds. You have the classical system. We've spoken about that already. The classical system uses the suffix "us" and "ik." When you use the suffix "us," it is referring to the one with lower valence. And when you use the suffix "ik," it is referring to the one with the higher valence. For example, you can name copper in two ways. Cu2O we call cuprous oxide, and Cu2O we call cupric oxide. And here you're seeing some of these elements there that have multiple valencies, and these are the only ones that have two different valencies. So copper, for example, has valencies 1 and 2, so always a higher valency is ends in "ik," so you call that cupric, and this will be cuprous. Iron, 3 plus, 2 plus, ferric, ferrous. Tin, 4 plus, stannic, 2 plus, stannous. Lead, plumbic, plumbous. Mercury, mercuric, mercurous. So the one with the higher valence ends with the suffix "ik," and the one with the lower valence ends with the suffix "us." However, in the classical system, it will not be applicable when you're having metals with more than two valencies. So before we go to that, let's look at how you know what Roman numerals correspond to the Arabic numerals. So these are the Arabic numerals here, and these here are the corresponding Roman numerals. Okay? So these are the Roman numerals that are used in parentheses depending on the charge on the metal line. Let's go see some now what you have there. Same thing here, showing you the upper and lower valencies for these ones. If you have this compound here, right, you'll have to decide whether or not this thing is standard or multivalent, right? You know that this calcium here is in group 2A of the periodic table. You can't call it calcium 2 because it will be redundancy to say it is calcium 2 because there is no calcium 1 or calcium 2. All right? Now in this case here, iron must be named iron 2 if you're using the stock system, right? Because in this case here, the iron must be 2 because you have two chloride ions there and each is negative 1. So they have two negatives on both of these. So this must be a 2 plus there. Okay? So you're saying iron 2 chloride to distinguish it from this guy here. Okay? Where now this guy is having a valence of 3 plus. Okay? And now you must write it as iron 3 chloride. Alright. So we go a little bit further down now. How do you name the nonmetals in binary ionic compounds? What you do here, drop the last syllable of the nonmetal in the compound and you replace it by "ide." For example, this is oxygen here. You drop that and you replace it by "ide." Sulfur becomes sulfide. So this is how you go. Nitrogen becomes nitride, phosphorus becomes phosphide, fluorine becomes fluoride, chlorine becomes chloride, bromine becomes bromide, iodine becomes iodide, and hydrogen becomes hydride. This some examples, some I give students to do here. How would you write the formula for, say, this one here? The formula will be, magnesium right away, determining whether this is standard or not. How do you know that? You know this is from group 2A, and you know the valence that this is going to have will match the group that is in. I told you that already. So this will be Mg2 plus. And of course, chlorine is more negative. So your formula is MgCl2. Now lead 2 iodide. They're giving you what it is, so it doesn't become difficult. So you know the lead is 2 plus oxygen is 2 negative. So it becomes PbO. And like that, you can write the formulas for the compounds there. They're giving you the valencies for these here already, unless they tell you it's us or ik, okay? You go ahead and you do that, write the formulas for that. So how do you go about naming binary ionic compounds in multiple valencies? So these are some guidelines that I give students. You ask a big question. The big question is, Is the valence on the metal ion in the compound multivalent or standard? Okay, so given a compound, you want to know whether the metal there belongs to the transition element. For example, this guy here. No. I pointed out to you that zinc and silver, apart from those in group 1A, group 2A, and group 3A, you have zinc and silver also have standard valencies. So in this case, because it is standard, it just says zinc oxide. This one here is, you see in this lead oxide there, we want to know exactly how you name that. You could have PbO is also lead oxide, PbO2 is also lead oxide. In this case now, you will see that this guy here is multivalent, all right? It's multivalent because it does not belong to those groups we talk about that have standard valencies. Now we know it's multivalent. We have now to also deduce its valency, or its valence. So look at this. So this is PbO2. Now that we know the non-metal there, and we also know which group it is from, and that leads us to knowing what valence it will have. So if you know the sum of the negative valence on this non-metal here, you will know what this is, because we said every ionic compound is neutral. So the negative charges on these atoms here must be equal and opposite to the positive charge on the lead here. So now we are having 2 oxygen ions, and each of them is -2. Therefore, you'll have a total of 4 negative there. Now to balance off this lead here, this must now be 4 positive, so that when you add these together, you end up with 0. And that is how you deduce the valence on the metal ion here. Now say it is lead 4 oxide. And if you want to use a classical system, because this is a higher valence there, you say plumbic oxide. Nothing is wrong with that. How do we know how to name this? First of all, find the total number of negative charges on the oxide ion, which we know belongs to group 6. Therefore, you have a charge of 2 negative. You have 3 of them, so it becomes 6 negative here. Whatever these are, how many, 2, 3, whatever, they must be equal and opposite to that, so it must be equal to 6 positive here. But now 2 of them are having 6 positive, so one of them must have 3 plus, okay? So then how do you name that? You say now it is ion 3 oxide using the stock system, or because this is having the higher valence, you say it's ferric oxide using the classical system. Nothing is wrong with that. What I give student here is this. I created this little table here for them to put a memory such that they're able to distinguish metal ions with standard valencies against those that have multiple valencies, these ones here, okay? And there's a large number here. These are a smaller number, okay? So if you can put these to memory, you can know which is standard, and you can pluck them out from a group of elements that comprise mainly of these ones here, or you can pluck one of these here from these ones here, all right? And here again you have some compounds here to name them. So what do you do? First thing is to determine whether or not the metal ion here is standard. This is lithium here. This is in group 1A, and this is oxygen. Oh, this is lithium oxide. Calcium, don't have to say anything. Calcium oxide. Aluminum chloride. Magnesium sulfide. Okay? This guy here is, now you have to know. Why? Because it does not belong to those that have standard valencies. So it's iron, but we know the oxygen is 2 negative. All right? So your friend here must be 2 positive here. All right? So how do you name that? Iron 2 oxide, or since it's a lower valence here, you call it ferrous oxide. So you can go ahead and practice those. The solutions to these are in the solution manual.